Okay, thank you, Antti. And now I'm going to take you to elevator world. So elevator design process based on simulated people flow. My name is Marja-Liisa Siikonen. I used to work in KONE Corporation for more than 30 years, and there with planning transportation devices in new buildings, but also control systems of elevators. I made a PhD thesis in 1997 about planning models for elevators in high-rise buildings. This thesis also includes artificial intelligence part, so already in 1990s. After retiring KONE, I established my own company, MLS Lift Consulting, and last year I published a book of people flow in buildings. How artificial intelligence has been used in transportation devices. The first ones were already 30 years ago in tall buildings, and how we there understood artificial intelligence was that it learned the traffic of the building by real-time control systems, and then utilized fuzzy logic to recognize traffic patterns. And later on, we used these traffic patterns also in design and in control forecasting future traffic. We can measure different things in our elevator systems. We can measure data from energy consumption, calls, and wearing of devices. But the main process that keeps elevators moving is people moving in the building. And that is why I'm going to talk about this basic process here. That is very important in many aspects. We started to measure the daily people flow in buildings with control systems, and then utilize the learned data in the control to forecast future traffic patterns, and then make different control actions according to the future traffic. But also when we obtained a lot of data from different buildings around the world, we got more information how the buildings work, and started to use this information also in elevator and escalator design. How people were counted in elevators, they were counted so that nobody knew that they were counted. So the control system used load weighing device. Every elevator has a load weighing device. It can be below the car floor, or it can be in the car sling above the car. There are different ways to measure the load. Also, there are safety rays or photocells in the elevator door openings to prevent that people don't get in between doors when they move in and out the car. So these are safety devices that every elevator have. So it was very beneficial to use these devices in counting people. Later on, there are more sophisticated methods like access control systems, destination call keypads, optical vision with video techniques, indoor positioning systems, mobile phones. that can be used in counting people. What we counted in buildings was the number of people moving in and out the elevators in both directions, up and down, and also for every floor. And then we gathered them in certain time intervals, let's say 15-minute or 5-minute time intervals. And then we obtained a lot of data, and it can be presented as it is here on the figure. So number of passengers per 15 minutes. And here we have time of the day, how many people enter the building is green, and red is how many people exit the building. Yellow is inter-floor traffic between floors during the day. So the control system measured this data for every day, but then it learned the data during the nighttime or depending on the system. But since the in real-time application, the call allocation makes decisions every or many times a second, so there is not so much time to make a sophisticated forecasts. So the simplest way is to use, for instance, exponential smoothing that takes the new data and combines it with the old forecast, let's say half and half every day to get a new forecast, and make this, for instance, for every weekday. Also, Bayes method has been applied to forecast calls. So these kind of control systems were installed in tall buildings, and we received a lot of data, but the profiles were always different. And to make them more comparable, we could scale the number of people arriving in a certain interval to the population in that area. And then we received data that had about the same peak heights. Here, for instance, in France, in a single tenant building, the peak height is 14. And here in Australia, office, the peak height is something like 12 during lunch hour. There are peaks during morning, lunch hour, and in the evening in offices typically. And if it's a headquarter type of building, there is a lot of interflow traffic, this yellow. So this kind of data we received, and this peak traffic, up peak, down peak, and lunch time peaks have been used in elevator design later on. But in the control, when we had a lot of data, numbers of people arriving and in each floor and so on, the control system has to know actually what type of traffic it is, if it's up peak, people enter the building, or is it down peak, people exit the building, or two-way traffic or lunch hour traffic, this kind of information. And there we used fuzzy logic. So for each traffic component, we looked if the portion of the incoming traffic is low or medium or high, and the same for each traffic component in the floor and outgoing. And this way, we used membership functions for these high, low, and medium to get change of traffic pattern smooth in the control system so that it doesn't jump immediately from incoming up peak to down peak, so that it smoothly goes from one pattern to another. Here is an example of a fuzzy rule that if intensity is heavy and portion of incoming traffic is high and portion of outgoing and interflow traffic is low, then we have up peak. So we could utilize simple rules to deal with the numbers. Here we have a layout drawing of a building, architect drawing. You can see there in the layout drawing, here we have escalators, here we have turnstiles, here is one elevator group, 6-car group, here is a 5-car group. So this kind of layouts we are planning when we plan building. So we or design how many elevators we should have, how many elevator groups we should have, how many escalators, and how many turnstiles, and then we place them in the architect drawing. And it's always a compromise between the space and price and service level. So it's a complicated design phenomenon that has to be repeated many times before the building is ready. In the let's say before software-based control systems, only up-peak traffic situation was used in the elevator planning. But when we got more sophisticated control systems with software, and also we couldn't anymore find out the performance from up peak only. So we had to simulate the traffic in the building to see how well they can handle different traffic situations. The simulators typically had used the event-driven modeling or continuous time-based modeling, and different types of simulations are possible. The simplest way is to use Monte Carlo simulation. Then there is a single elevator group traffic simulation, building traffic, or people flow simulation that includes both vertical and horizontal simulation, and pedestrian traffic simulation. I go through these examples, 5 examples, in the next slides. Monte Carlo simulation is a way to calculate and simulate random traffic. So in this case, it when we define a parameter like round trip time, the time when the elevator goes up and down, how long it lasts, we generate a random passenger traffic in Monte Carlo simulation to determine the number of probable stops for the elevators. And then we using kinematic equations, we can calculate the round trip time. So this system is based on probability theory only. It doesn't have any control systems. But in this second slide, we have elevator group simulator. It is called Elevate from Peter's research. And most of the consultants, elevator consultants in the world at the moment use this one. So there we model the building floors and populations per floor, and then generate what this has, what the other didn't have, or the previous one didn't have, is that it has a generic group control system that allocates the landing calls to elevators. The elevators are here. So when passenger arrives to a floor, he gives a landing call, and then there is a control system that allocates this landing call to the best car in the group. And in this simulator, we can generate daily traffic peaks to find out how well this elevator group can handle the situation and what the passenger waiting times are. This is a bit more sophisticated simulator from Kone, building traffic simulator. There we can simulate all transportation devices in the building. Here we have escalators. Here is an elevator group in 3D. This is a two-dimensional view of the elevator group. And there we feed the traffic into the building, not only to elevator group, but the whole building, and see how well the given transportation devices can handle the traffic. Also, we can use it in evacuation studies to find out how fast the building can be evacuated. This is Kone People Flow Simulator. How it what is different from the previous simulator is that it includes also horizontal traffic. It can simulate vertical traffic, but also horizontal traffic in plane. So we feed in the simulator from architect building information models, the walls and all let's say corridors, access gates, whatever there is in architect drawing, we can feed as input in the simulator, so we can draw the building as accurately as possible, and then feed the passenger traffic in the building. People move horizontally in the plane, and where they avoid colliding walls or each other or access gates, they move from what we call hotspot to another. So we define as hotspots, let's say building doors, reception, access gate, elevator group. So the passengers choose the hotspots that are in their routes and move from freely from hotspot to another. And this way we can simulate also horizontal movement and vertical movement, and find out if there are bottlenecks in the building design, transportation design, so that the people have to queue. This last example is called a mass motion. It's a software from a world famous design and architect company, Arup Group Limited. They use this simulator in planning, for instance, railway stations, shopping malls, cultural landmarks, and also use it in evacuation scenarios. They also feed first the building information model in the simulator, and then feed traffic and see how well the people fit and how well they are served, if there are queues like we can see here. And they have their own experimental people behavior models in the simulator. This example shows that we can detect the heat maps in a real building, so that if we, for instance, use 3D cameras, they can see the locations of the agents, and then when they move in the building, the agent paths can be rendered from the two heat maps as this, and we can see where the bottlenecks in a real building, existing building are. So what to do next? How can we improve and make even smoother people flow in future buildings? Is that we can utilize the new sensing systems as much as possible to detect people flow, and then utilize this detected people flow in new ways in control systems, and also guidance in guidance of people, so that they can easily find to their destinations. When we measure more and more buildings and get the traffic, how it is in certain types of buildings, we can use them in building design better. But for this, actually, we should standardize the inputs, and so that when we have different simulators, if the input of people flow would be the same in each simulator, the simulation results would be more comparable. We have an ISO standard that appeared in 2020 that standardizes the procedure in planning elevators with simulation, but the actual models, let's say passenger generation and these inputs for traffic flows, have not been standardized yet. This concludes my presentation now. Thank you.